Thank you, Chi, and hello, I am Wendy, and today I will be talking about our findings and interpretations of prehistorical earthquake ruptures along the Dzhungarian and the Lepsy faults in Kazakhstan. As we know that earthquakes occur very often at the plate boundaries. In fact, many earthquakes also occur within the continent, and they could also be devastating. Actually, intraplate earthquakes have killed much more people over the past century than those happened at the plate boundaries. This is mostly because intraplate earthquakes are more distributed and unexpected. So it's important to study more about the fault behaviors and the earthquake occurrence inside the continent. And Tian Shan is one of the most active intracontinental seismogenic belts. In Tian Shan, several great historical earthquakes with magnitudes higher than 7 have occurred previously, as those red dots here. Also, large faults can be clearly recognized due to the well-preserved landscape in such an arid region. Despite the widely spread instrumental seismic records in Tian Shan, we have found that there are apparently fewer records at the northern tip of it. This northern region is called the Dzhungarian Aletal. We have found large textural straddles fault, which is called the Dzhungarian Fault, and another shorter fault called the Lepsy Fault bounding this mountain range, but no large historical earthquakes here. More importantly, hundreds of kilometers long surface ruptures of the two faults can be easily recognized like these from the imagery. And these make us curious about how big earthquakes could be in this region and what the fault depth and the rupture length could possibly be in the most recent events. To answer these questions, we use topographic analysis as the main approach to measure the offsets and the ruptures. We also have several samples for quaternary dating with additional morphological scarp dating results to help define the timing of the rupture. The topographic imagery we used include the digital elevation models and the orthorexite photos from both the open source and self-produced products. We use these imagery to map out the faults and identify geomorphic features. The self-produced imagery, including those made from the Pléiades satellite imagery and the drone images collected in the field, and they have higher resolution. Here you can see the differences between low and high resolution images of the same fault scarp, and we mainly rely on the high resolution ones for measuring the offsets. And first, let's look at the mapping results of the Lepsy fault, which are in the red lines. It is a right lateral straddling fault with reverse components. The purple dots indicates the lateral offset features that we found, and the different color of the purple dots indicate the different amount of the displacement. Actually, the digging angle of the Lepsy fault and its fault depth have been reported by Campbell et al. With an inferred average depth from 8 to 14 meters and with an average slip vector azimuth of 330 degrees in the most recent events. Since the length of the Lepsy fault is only 120 kilometers, this makes the slip-to-length ratio for the Lepsy faults larger than 10 to the -4, which is abnormal in terms of the global earthquake scaling. Campbell et al. Also suggests 2 earthquakes might have occurred along the Lepsy fault within the 5,000 years and within 400 years, respectively. And the eastern extension of the Lepsy fault is the Dzhungarian fault, which is the main boundary structure in the northwestern Tian Shan. However, the two faults are not directly connected. In the area between the two faults, there is a site at the east of the Tantak River that has over 8-meter high fresh fault scarp, which is similar to the maximum vertical slip found along the Lepsy fault. Also, these scarps show a single step with steep slope angle, which means they are possible to be single event scarps. Because of this, we decide to try applying morphological scarp dating on them. The principles of morphological scarp dating assume the scarp degrades as a simply diffusive process, so the shape of the scarps could indicate their forming ages. Because of this assumption, this method is theoretically only valid for single event scarps. Usually, the smoother the scarp is, the older each age will be, but it also depends on the rates of diffusivity, which varies in different regions. And we use the rate here inferred from the neighboring Xinjiang region. This method has great uncertainty. However, it could provide some hints when there aren't many clues from the quaternary dating result, which is the situation in the Dzhungarian region. And the morphological dating results indicate these scarps are between 3 to 2,000 years old, which match with the timing of the older events suggested for the Lepsy Fault. Now we move further east to look at the Dzhungarian Fault. This is the mapping overview of the Dzhungarian Fault, which is marked by orange and brown lines. It's marked in different colors because we had found that fresh ruptures only appear in the south of the Tentek River. This is based on the observation of fresh and degraded scarps across this boundary. In the north of the Tentek River, scarps are highly degraded with no offsets among the youngest fans, but in the south of it, fresh scarps clearly appear at the range fronts that afflicted the youngest alluvial fans. Besides this, another important observation is that the vertical and lateral offsets distributed unevenly throughout the fault, which shows the northern part has oblique slip components, whereas the southern part is almost pure strike slip. We think this could result from the faults that changes its strike for about 20 degrees in the middle. So based on the morphological characteristics, the width of fault zone, and the distribution of offsets, we divided the Dzhungarian faults into 8 sections, and we inspect every section for finding out the offsets in the most recent events. We start our investigation from the southern sections because pure strike slip offsets are easier to be measured from the displaced river channels. For horizontal channel offset measurements, we set the maximum, the preferred, and the minimum value to be the distances between the outer levees, the middle, and the interlevees of each channel. We also categorize them into different qualities based on their polarity, sinuosity, and obliquity. First, we look at the southernmost section 7. The offset channel do not have good qualities here because they intercept with the faults obliquely. But we can still find the smallest offset in this section to be 6.9 to 8.4 meters, with some cumulative ones over 50 meters. And moving north to section 6, there is no obvious offset features that could be measured, which is probably due to the agricultural activities in this region. But we do find fault traces and a likely fresh Port Bahar Basin across the field, showing the fault exists in this section and it did rupture previously. And now we're moving north to section 4 and 5. We found offset features with good qualities that are widely spread along these 2 sections. And the smallest offsets measured from a single fault strand is 6.9 to 8.6 meters across the 2 sections. Since there is no historical core seismic data along the fault, we could only assume the measured smallest offset is the offsets in the most recent event. And if assuming a fully locked fault with a constant slip rate, we should be able to see cumulative offsets that are common multiples of the smallest offset. So apart from only taking the results from the individual measurements, we also use a stacking method to help figure out the most recent event offsets statistically. We do this to section 4 and 5, where we have the most dense and high quality offset features with similar amounts of smallest offsets. We first plot every measurement into triangles that have different shapes to represent both the preferred offsets and the uncertainty for each measurement. And we stack all the triangles into a cumulative probability density curve to see what the peak values are. It shows 3 peaks at 8.8, 15.2, and 23.7 meters, which indicates the fault slip in the last 3 events are 8.8, 6.4, and 8.5 meters. These values are very similar to what we found from the individual measurements. And they are also similar to the smallest offsets observed in section 7. So because of the similar smallest offsets across the pure stratigraphic sections, and because we found fresh ruptures do go through section 6 as well, we suggest the pure stratigraphic sections from section 4 to 7 to be one fault segment during the most recent earthquake, and the fault slip on the segment should be 6 to 9 meters. However, it's hard to directly measure the fault slip in the northern sections that have oblique components, not to mention that the northern sections tend to have branches. Let's look at section 3 first. Section 3 is the large slip partitioning zone with two main branches. The northern branch is dominated by vertical components, whereas the southern branch is dominated by pure streak components, with the smallest offsets also around 8 meters. The branches and many splays make the geometry of section 3 the most complicated one among all the sections. Moreover, we find a fresh fault apart basing on the southern branch. Here is what it looks like from the Pléiades images and from the field. We measure the scarp heights to be mostly 8 to 12 meters, but we do not have good quaternary dating samples of it. So we also try to do morphological scarp dating on these scarps, and the results indicate they are 6 to 3,000 years old. Now moving north to section 2, which is the closest section to the Lepsy Fault. We found there is one main fault trace with a few small splays. It is also noticeable that lots of fresh scarps appear at the range front, just like the Lepsy Fault. A typical example is at the Bear River site. Here we can see 6 to 8 meter high scarp appear at both younger and older terraces, as you can see from the field photo 2. Also, the smallest lateral offsets is 12 to 16 meters along the main faults at the site. We have a radiocarbon sample collected from a snail at the terrace riser, and it indicates the terraces were formed around 400 years ago. However, morphological scarp dating shows these scarps are 7 to 4,000 years old, which is largely different from the radiocarbon one. And about 1 kilometer upstream of the Bear River sites, there is another fresh scarp that is about 4 meters high on a smaller splay. Here, the radiocarbon and the morphological ages match with each other. Infer the scarp should be around 4,000 years old. Now we can only use the current information mentioned above for estimating the most recent event offsets for section 3 and 2. Different from directly taking the smallest offsets for the pure stratigraphic sections, we calculate the most recent earthquake offsets in the northern sections by simplifying the fault's geometry into one fault plan first. And second, we assume a constant slip vector azimuth through the faults derived from the pure stratigraphic segments, so that we can use the observed minimum lateral and vertical offsets on each section to estimate the total fault slip along the fault plane in the most recent earthquake. And here are the results for each section, including the previous finding for the Lepsy faults and the one at the Tantek River East site. If we plot the distance along the fault against the total fault slip during the most recent event, we can see that the largest offsets appear on section 2 and probably section 3 as well, which might be due to the fault's geometry. And the next question is, could the Lepsy Fault and the Dzhungarian Fault have ruptured together? In this study, we only have radiocarbon samples, which are actually collected from snails that we are not sure if they can really represent the age of the terrace abandonment. And our morphological dating results show the scarps along the Dzhungarian faults is 7 to 2,000 years old, but we know that this method has huge uncertainty. From previous studies, ages from Campbell et al. Suggest two events on the Lepsy Fault occurred within 5,000 years and within 400 years respectively. There is another change in data on section 7 indicating 4 paleo-earthquake events, with the most recent one occur within 6.6 thousand years. In fact, we also did morphological scarp dating for the previously measured scarp at the western tip of the Lepsy Fault. The site is called Ayako, and the scarps were inferred to be single event scarp from previous study. The results are consistent with the Dzhungarian morphological scarp ages and one of the two dated events for the Lepsy Fault from Campbell et al. Therefore, although the ages from different methods are not always compatible and we have limited constraints on the timing of the most recent events, the majority of the available evidence is consistent with a single rupture along the two faults that displace terraces, which are as little as 4,000 years in age. In fact, many fresh fractures are distributed in the transition area between the two faults and also appear near section 3 as well. And clusters of large landslides can also be found near section 3 as where these small pink triangles are, which might possibly be caused by large earthquakes too. We also noticed that the slip vector azimuth of 328 degrees inferred from the pure strike slip segment is very similar to the 330 degrees estimated for the Lepsy Fault from previous study. So it is likely that the Dzhungarian Fault and the Lepsy Fault is a fault system that could rupture together and cause the ruptures in the area between them. We name this as the rupture scenario 1. And using the fault parameters we have calculated with the assumption of the seismic depth from 15 to 30 kilometers, this scenario 1 could cause an earthquake around magnitude 8 with an upper end to magnitude 8.4. We also propose a rupture scenario 2, considering if the Dzhungarian Fault only ruptures alone. In this case, the potential earthquake moment magnitude could also up to 8.2. And of course, we are aware that the scenarios with shorter rupture length and fault slip are also possible, but we'd like to emphasize on the likely upper end magnitude and rupture length in this region, which could be over 370 kilometers long. We have mentioned that previous study points out the Lepsy Fault has abnormally higher slip to length ratio from paleo-earthquake study. However, if the Lepsy Fault does not rupture alone, but ruptures together with the Dzhungarian Fault as the rupture scenario 1 in this study, it will yield a slip to length ratio within the normal range. We also plot other large historical earthquakes of both intraplate and interplate events in this figure. And we found the intra-continental events do not tend to have higher slip to length ratio except for those few high-stress drop ones. To sum up, we found the fault slip and the possible rupture length for the most recent events occurred on the boundary strike slip faults at the northern Tian Shan. Although large uncertainty exists, the faults are likely to trigger earthquakes that have magnitudes over 8. Also, the Dzhungarian Fault and the Lepsy Faults might rupture together, which also means that the ruptures do not propagate north along the general strike of the Dzhungarian Fault, but instead, they go along with the misoriented Lepsy Fault. In fact, the ruptures are likely to start on the Lepsy Fault and propagate southwards, because the Lepsy Fault might be the primary mountain building structure in this region, as it has similar trend with the east-west oriented ridges of the Dzhungarian Alatau. This further implies that a major boundary fault in this region could have a joint rupture with a shorter local structure, which is still likely to trigger larger magnitude earthquakes than expected for single fault ruptures. And that's it. Thank you very much.
Thank you very much, Wendy. That was a great talk. So this is the time to remind everybody to put your questions into the chat, so Wendy will have time to read them as Aisling presents the next talk, and we'll keep all the question and answer to the end, till after Aisling's presented. So yeah, if Wendy could stop sharing, and oh no, this is already okay. Aisling's slides, great, thank you very much. And so Aisling, okay, is a final year PhD student at the University of Cambridge, and she's also an active member of the COMET community. Her research focuses on the active tectonics of the Earth's continents using a variety of techniques, including earthquake seismology, structural geology, tectonic geomorphology, and dynamic modeling to assess continental deformation over varying temporal and spatial scales. She collaborates with industry, ERAP, to use her research as a step towards mitigating the seismic hazard posed to communities around the world, with a particular focus on increasing the resilience of the built environment to ground shaking earthquakes. So the title of her talk today is Seismotectonics of the Northwest Himalayas with Insights for Seismic Hazard. The time is yours, Aisling.
Great, thanks, Chi. So we're going to move away from Central Asia now to Southern Asia. And today I'm going to talk about the geometry of active shortening in the Northwest Himalayas and what implications this has for the seismic hazard in the region. And the work that I'll be presenting here today has been done in collaboration with Professor Alex Copley at Cambridge, Dr. Salman Puney at Leeds, and Professor Subra Maitra from ISERC in Kolkata. And of course, this work wouldn't be possible without the funding from EPSERC, ARP, and the Royal Society. So the motivation for our work stemmed from an earlier PhD project where we assessed the regional scale controls on earthquake ground motions in a generic folding basin setting. We found that the amount of initial ground motion produced largely depended on the source depth, but how much of this energy got dispersed depended on the basin structure. So that's either the basin depth or width. We've seen that the greatest amplification in these ground motions was produced when the ratio of the surface wave wavelength was equal to the basin depth. And we want to apply what we learned in this generic basin study to a particular region where we don't really know much about the hazard. So what we did is we applied it to a site-specific study in the Northwest Himalayas in one of these known apparent seismic gaps. And we had both some local and some general aims for the project. Firstly, specific to the area, we wanted to identify the active tectonic structures, see what's currently active, and what estimated ground motions there would be if the main Himalayan thrust beneath Jammu were to rupture. And hopefully that would improve our understanding of the current hazard there. Our more wide-ranging aims then was to investigate the relative ground motions between different fault geometries, because we know it varies along strike along the Himalayan arc. And also what effect would it be if the Himalayan thrust only partly ruptured like Gorka, or if the entire thing ruptured. So we had a few different aims going in. So to give you a bit of context about the geology in the region and why we picked this area, firstly, we know that large thrust faults accommodate convergence between India and Tibet along this southern margin, just along here. And they have a history of producing great earthquakes with widespread damage. Some of the largest ruptures are shown in this Billen figure in these black rupture patches. And along most of the Himalaya, there's geomorphological evidence that these thrusts can rupture to the surface. But in the state of Jammu and Kashmir, which I've circled here in red in the north, the thrusts are buried, and large-scale folding is the only expression of active deformation at the surface. So this makes it difficult to assess the seismic hazard there. The depth to the main Himalayan thrust beneath Jammu has been reported to be between 2 and 10 kilometers. And given our findings from our original study, changing the source depth by a couple of kilometers can have a large effect on the ground motions. So we wanted to better constrain this, and in order to do so, we went out and did some field work. We looked at seismology and also the geomorphology. So on a local scale, the region is shortening at roughly 11 to 12 millimeters a year, and this is from a combination of both faulting and folding. This Pléiades fault system, which is denoted by this RF here, is supposed to be, or is suggested to be, the most active structure in the region, and it accommodates 6 to 7 millimeters a year. The Shurmaskar anticline, which is this large-scale fold, which I investigate in this study, it accommodates essentially the other half of the shortening. And since we did the fieldwork in December 2019, we looked along essentially this transect of the entire fold along strike. And what we've seen was anything sort of east of Pléiades didn't look active. We didn't see like offset fan surfaces, river terraces, false scarps, they all seemed intact. So what we think might happen, or what's happening, is that this shortening has been transferred further south onto the Seismotectonic decline. And of course, it could be transferred onto the main boundary thrust or the central thrust, but due to the lack of documented active faulting, we think it's been transferred to the Seismotectonic decline and the faults beneath it. So in order to get a better picture of the subsurface geometry, we looked at different techniques to get a more rounded picture. So we looked at the structural geology, which you can see nice dipping beds in this fold here, the river terraces, and using geomorphology, and then of course the earthquake seismology. So firstly, the structural geology. It's mainly characterized by long wavelength folding, and the fold itself is about 120 kilometers along strike and 40 to 50 across strike. And it's made up of what's known as schwallic sediments. And these are interpreted to be the sequence of foreland basin sediments, which were laid down during the encroachment of the Himalayan mountain belt. During our fieldwork, we traversed several of these sections and took these bedding and lineation structural measurements to get an overall understanding of the structure. And I've made these interpretive cross sections from that. Our data shows that there's shallow dips on the outer limbs of the fold with a pattern of increasing dip towards the core, where there's this abrupt change in the Jungian direction, and it has a near isoclinal fold core for 3 to 5 kilometers or so. We believe this fold geometry is likely to represent lower portion of liftoff folding, and I've sort of drawn a little schematic which tries to explain that. And it's just produced from a shortening above a weak decoupling layer. And assuming this geometry means that we can't estimate the total amount of shortening across the region. However, we can estimate the depth to the decoupling layer, which we assume to be this 6 kilometers, which you can see here on our cross sections. And this is because we assume the deepest competent layer is this middle schwallics, because we didn't see any deformation in the field. It's these massive sandstone layers, and it was very different to the less competent mud rocks in the region. So we also located a minor fault on the northeast flank of the Seismotectonic decline near the village of Dzhungarian, shown here. And the red triangles just show this extent of the scarp, and it's roughly about 15 kilometers along strike. And it trends northwest southeast, parallel with fold. And although in the field we weren't able to establish the dip direction of the fault, we were able to use the satellite geometry or imagery to make a DEM and work out the south side up motion, which is roughly 7 meters or so in the terraces. And we were able to do it on both either side of this river here. And the dips that faulting in this location is consistent with the accommodation of a change in dip in the fold or in the fault surface, where it becomes steeper to the northeast. And then what we did next was look at the geomorphology, and that decline itself is cut by a number of southwestern rivers that preserves late quaternary terraces. And we specifically looked at 3 rivers in detail, which cross-cut the fold. And here I've just shown one for the River Uge. And what we did was we compared the terrace heights above the present day riverbed as a function of distance perpendicular to the fold axis. So you can see that here. And the river is shown here in blue, with the terrace, the edges of the terraces shown in these colored lines. At the southern margin of that decline, what we see is a terrace level increase to about 15 to 25 meters over a horizontal distance of 2 kilometers, which we assume is tectonically uplifted, because at that point in the river, it's such a sudden change that given a wide low gradient river valley, it doesn't seem like there would be enough energy if it wasn't tectonically derived. The terrace height then remains roughly constant in height across the southern limb, with a slight increase in elevation towards the core, where we have few terraces, again, because of this highly erosive landscape in the core. The northern limb, the terraces then increase in height with distance along profile, which implies an increasing uplift rates to the northeast. And then this overall, from the geomorphology overall, we think that this constant terrace height across the southern limb implies that that uplift isn't due to folding, but instead due to a single planar fault at depth. So that's what we determined from the geomorphology. Next, we looked at the seismicity across the region, and I modelled earthquakes equal to or greater than magnitude 5 to get better estimates of their earthquake mechanism, but particularly the earthquake depth and dip, because from our previous study that showed that they had the major control on how much ground motion was produced. So we want to get better estimates of those. I used different methods, including long period, broadband, and short period body waveform modelling, which just involved techniques of fitting recorded seismograms to synthetics. And based on the events, which we can show in the map here, it's just a zoomed in area again, our fold is here, and this is the cross section. What we see is that the depths range between 3 and 16 kilometers, with one deep earthquake shown down here near Kangra. And the dips are mainly sub-horizontal, gently dipping out in the southwest at the range front, and they steepen northwards towards the Kishvar window area. And this is consistent with the microseismicity studies in the region, which are shown in these grey dots and green dots. So overall, the various techniques showed us that in local to Jammu, we can constrain the depth, the structural depths through geomorphology and seismology well, but then the teleseismic earthquakes can help us constrain the far field structure of the Himalayan thrust. We were able to use the morphology of the terraces to determine the shortening style in the region by using the length scale over which the terrace height decreased. And using this methodology, we were able to determine the up-dip termination depth of this fault. So we know it's roughly buried at 2.5–3 kilometers depth. Assuming published ages of 10 to 12 or 1,000 years for the river Uge terraces, we can determine uplift rates in the order of 0.5 to 1.5 millimeters a year, and horizontal rates of 6 to 15 or so. And what we can determine as well from the terraces, from all the rivers we looked at, not just the one I've shown here, is that the fault is buried at 3 to 12 degrees across the southern limb, and then increases in dip across the northern limb to 12 to 24 degrees. So there's this slight increase in dip coincident of where those terraces increase. And how I've shown the seismological earthquakes, or the teleseismic earthquakes, is just I've plotted their nodal plane dip, and then I've scaled them by their seismic moment. So that helped me determine and essentially match up what I could tell from the structural and the geomorphology with the far field and infer in between. So what I did then is I used the observations to inform a 3D wave field model. And this was designed to replicate the present day configuration of the Northwest Himalayan range front. We imposed an elliptical slip distribution with 8 meters of peak slip at the center to replicate the current slip deficit that we think is in the Northwest Himalayas since the last major earthquake in 2005. And we constructed different thrust fault geometries based on different parts of the Himalayan range front. So the top here represents Nepal, where we can get surface rupturing earthquakes. The middle here is a shallowly buried fault like Jammu, and the bottom represents somewhere like Eastern Pakistan, where there's still this basal fault. And I ran each of these models, and what we found was that the surface rupturing model produces the highest peak ground velocities, which we would expect, with in excess of 5 meters per second. And this is roughly 18% higher than the shallowly buried fault. So just changing that by a couple of kilometers caused an increase of 18%. And similarly to the deep basal fault, this was 20% higher. So it really shows that this really shallow fault geometry could have a large effect on the ground motions. Similarly, we conducted models where we just ruptured the upper portions of the fault and then the lower portions, similarly to the 2015 Gorga earthquake. And in each of the simulations, I kept the velocity structure, the rupture process, model to me, and everything the same except for the depth extent of the rupture. So here I ruptured the entire fault, here just the upper portion, and here the lower portion. And I think from this, what the most striking result was is how comparatively small the peak ground velocities for just the lower rupture was. So the peak ground velocities generated for the lower rupture, which is this one at the bottom and the green line on this figure, shows that it's only, well, I say only, it's roughly 1.5 meters per second. What we see is that the upper fault rupture or the entire fault rupture can generate peak ground velocities that are over 3 times larger. So this really has implications for hazard and what could happen in the region. But again, these are all relative peak ground velocities. This isn't, what will happen or anything. Although I've modeled these, we know that a more serious scenario could be that if a magnitude 8 earthquake were to rupture the whole fault from the base of the lock zone. And what I would say is like the peak ground velocities generated by the shallow rupture are similar in amplitude and still poses severe hazards. So we should be thinking about that. So just to summarize, and our take-home points are, we know that we've used the seismology and geomorphology to constrain the down dip structure of the main Himalayan thrust in and around the seismic gap around Jammu. We know that the main Himalayan thrust doesn't reach the surface in the region, but it is shallowly buried at 2.5 kilometers depth. And our seismic wave propagation modeling was able to determine that faults that rupture to the surface can generate peak ground velocities that are 20% higher than those that rupture on buried faults. But similarly, if we rupture the up-dip portions opposed to the lower portions with an equivalent magnitude, it could produce ground motions that are 3 times higher. So overall, our take-home message is that our results indicate that accurate constraints on the shallow geometry of thrust faults around the margins of mountain belts are required for estimating seismic hazard in these critically exposed and rapidly urbanizing regions. So that's me.
Great. Thank you very much, Aisling. Cool. Now is the time for Q&A. So people in the audience, if you have questions, please put in your questions into the chat box and then we can start chatting. So maybe I'll start with a question. I actually have questions for both of you. I'll start with a question for Wendy. You mentioned you found clustering of like small, medium-sized and large-sized horizontal offsets, and then also like a small, medium-sized and large-sized vertical offsets. Do you find those small horizontal and small vertical offsets to be close to each other in space? Like,
do you mean?
Yeah, like.
Do you mean? Sorry, you go first.
Do you tend to measure small vertical offsets? Maybe just by the size of a small horizontal offsets, and then do you tend to get large vertical offsets by a channel that has recorded a large horizontal offsets, for example?
So I think you mean the northern sections that have oblique components, right? Because yeah, so actually no. So actually, where we measured in the northern section, the lateral offsets and the vertical offsets we measured are quite large, even they are the smallest that we can found. I mean, this is on the main fault. I mean, we do find like smaller vertical offsets on the small splays, but it's quite obvious they are just splays, but not on the main fault. So yeah.
Okay. Cool. That's interesting. And then also you mentioned you've segmented your faults into and then analyzed the clustering of offsets section by section. So what do you base your segmentation on?
Right. So when we do the separating the sections, we first don't see those sections as the fault segments. We just categorize them based on their morphological characteristics, which including the width of the fault zone and the strike, and also like if they are pure strike-slip or if they are applique-slip. So it's quite interesting that, for example, in section 4, actually, the strike changed about 20 degrees from the south to the north in the section 4, but section 4 remains the narrowest among all the sections. So in this case, we still categorize it into one section. And then we further inspect whether those sections could be fault segments. And we found that the southern pure strike-slip sections could possibly be one fault segment. This is mainly because they have similar smallest offsets that we found, and they are in general very continuous and do show fresh ruptures among them. And in the northern sections, since section 3 and 2 has very different geometry, we think they are separated fault segments. But according to what we've while our like dating ages and including the combination from the previous study, we still we think those sections might rupture together, even if they are different fault segments.
Cool. Yeah, great, thanks. And then I guess I also have questions for Ashley. So in your introduction, you said you work close with Arab, and I remember you worked at Arab before starting the PhD, is that right? So like, I guess my question would be, what is like to work on a PhD project that has close link with a industry, or were you trying to like actively maintain those link with the industry, and how do you see this transfer of a research outcome into industrial applications?
Yeah, no, it's a good question, because it's really important that we chat to each other, because what we do really feeds into their work. So my research on the earthquake ground motions and just essentially better understanding the possibilities in these regions that we just have very little data on, they use in their probabilistic seismic hazard models, essentially. So they'll run a series of models probabilistically alongside my physics-based models, and it's sort of used to ground truth different faults that we may think are active. More recently, I've been working on looking at how the damage distributions to buildings are affected by these different scenarios with earthquake ground motions. So that's something that they do on most projects, essentially, because you have to run it for any sort of proposed building project. But it's been, for me, I think it's been a really positive experience, because you've had people that can inform, as you do the research, what would be useful outcomes, or to kind of streamline what's useful to produce for them to then use in the real world, shall we say.
Yeah, certainly. Yeah. And then since you found that the ground motion will be so different whether or not you rupture the upper portion, how would you suggest this can be factored into their probabilistic models?
So I think it's just an awareness of knowing the resolution now that they really should take into consideration. So if they're looking at a particular region and we look at the, say, top 40 kilometers, assuming that's the crust depth, it's really saying that, oh, we need to have enough data, or maybe do reconnaissance fieldwork or something, to then understand that top 5 to 10 kilometers better, that we can't basically ignore it and assume it's the same as the next 10 to 20, because we've shown that it makes a really big impact on the ground motions. So I think it just helps direct where they need to put their resources, essentially.
Cool. Do you know what this? I'm sorry.
No, I was just going to say, I have a follow-up question, if that's okay. Because I was going to ask this to sort of tie them together. Aisling, what would you suggest is the minimum amount and type of information that you would need to start doing an analysis like yours, in a way that, like, what could Wendy, for instance, be looking to accumulate in terms of data if she wanted to better understand the Dzhungarian fault system in the way that you understand the frontal thrust system?
That's a good question. The first problem is there's usually not a lot of data that we have, or we have it, but it's very sparse, so it's not consistent, and there's no baseline marker. So the first thing I would always do is make sure you have data across different sources. So if you try to get geodetics, seismology, paleoseismology, something, because they'll all give you an indication of different points in time. So I'll always use the seismology or damage records or intensity records for the historical data. But then, of course, like Wendy uses, the quaternary terraces, scarps, everything for the more recent, and that can give you a time history. So that's the first problem. But then spatially, I think spatially is just different, because it'll be really concentrated probably in cities, and then you'll have like nothing out towards the range fronts. So I always think, get your hands on any data you can, see what it kind of says together, and then use modeling or some sort of like deterministic approach for the places you don't have observations, and use like examples like Gorka or something that was similar in the setup to fill in to try and give us our best estimate. That's my approach, but I don't know if it's right.
That's great. Sorry, G, I have one follow-up question to that. If you had unlimited money, what would you try and collect for, like, making it the best model you can, like you've made? I'm sort of thinking maybe from your conclusions that trying to constrain the geometry is what is most important. But
yeah, if I had unlimited money, I would do shallow seismics across the entire Himalayan range front, and we would have an insane velocity model, because I think that's one of the key inputs for any of these physics-based models. It changes a lot with the velocity model, and sure, we've got VS30 models and everything now, but actually we need 30 to like 10 better. So yeah, and shallow seismics is expensive. So yeah, if I have unlimited money, I would do that.
Cool. Maybe actually I might throw that question to Wendy as well. If you had unlimited money, what would you do for the Dzhungarian fault to better understand it, and Lepsy fault?
I think I really want to collect more samples and use more cosmogenic nuclei dating samples, or like whatever we could do in that region, because it's really hard to do radiocarbon stuff. And then yeah, I think I will try to use money on the age constraints.
Sounds great.
Thank you.
Perfect future scenario when we have a dating sample from each channel, each scarp. Cool. Not sure if there are more questions coming from the audience, but then like we are getting towards the end of our webinar today, and I would like to thank both speakers for today, and also thank the audience who are watching. And we will confirm the speaker for the September webinars soon in mass email you will receive. And shall we Have I missed anything, Tamara?
No, that sounds great. I just a final thank you to our speakers for coming along and agreeing to present your wonderful research.
Yeah, and all the best for finishing your wonderful PhD project.
Thanks, thank you. Nice to see you.
Nice to see you guys too. And thank you everyone for coming.
Bye.